Okay, hi Michael.
Hey, Charles, how's it going?
It's going pretty well. How's it going in your end of the world?
Very nice. What do we want to talk about today?
Well, today we are going to talk about supervised learning. But in particular, what we're going to talk about are two kinds of supervised learning and one particular way to do supervised learning. Okay, so the two types of supervised learning that we typically think about are classification and regression. And we're going to spend most of the time today talking about classification and more time next time talking about regression. So the difference between classification and regression is fairly simple for the purposes of this discussion. Classification is simply the process of taking some kind of input, let's call it X, and I'm going to define these terms in a couple of minutes, and mapping it to some discrete label, usually for what we're talking about, something like true or false. So what's a good example of that? Imagine that I have a nice little picture of Michael.
It looks just like me.
It looks exactly like you. So I have a nice little picture here, and I want to know whether this is a male or a female. So given an input like this, I will map it to male or female. So what do you think, Michael? Do you think this is a male or a female?
So you're classifying me as male or female based on the picture of me, and I would think,
Right.
Based on how I look, I'm clearly male.
Yes, in fact, manly male. So this would be a classification from pictures to male. The alternative would be something like a picture to female. And I'm just going to take a completely stereotypical image of either a female or
I think
I don't know.
that's actually me when I let my hair go long.
Right. So which points out that this can be pretty hard. But this is what we're going to spend most of our time talking about at first is the classification task. So taking some kind of input, in this case pictures, and mapping it to some discrete number of labels, true or false, male or female, car versus cougar, anything that you might imagine thinking of.
Car versus cougar.
Yes.
I guess that's an important thing if you're driving. You don't want to run into any cougars or probably other cars either.
Well, you're sitting down and you're trying to decide whether you should ride this thing that you see or not. And if it's a cougar, maybe you don't want to, and if it's a car, maybe you do.
Excellent. Don't drive a cougar.
Don't drive a cougar. That's the first lesson in machine learning.
Excellent.
Okay, so that's classification. We'll return to regression in a little bit later during this conversation, but just as a preview, regression is more about continuous valued functions. So something like given a bunch of points, given a new point, I want to map it to some real value. So we may pretend that these are examples of a line, and so given a point here, I might say the output is right there. Okay, so that's regression, but we'll talk about that in a moment. Right now, what I want to talk about is classification.
Would an example of regression also be, for example, mapping the pictures of me to the length of my hair, like a number that represents the length of my hair?
Absolutely. And for the purposes of the sort of things that we're going to be worried about, you can really think of the difference between classification and regression is the difference between mapping from some input to some small number of discrete values, which might represent concepts, and regression is mapping from some input space to some real number, potentially an infinite number of real numbers.
Cool.
So
let's do a quiz to make sure we get
okay,
this.
I like that. So we've talked about classification and regression and gave a couple of examples of each. So now I want you to take a moment to make certain that you understand the difference because it's a crucial difference for supervised learning. So here's a very short little quiz. You have 3 questions here, and we've divided the world up into some input to some learning algorithm, whatever that learning algorithm is, the output that we're expecting, and then a box for you to tell us whether it's classification or regression. So the first question, the input is credit history. Whatever that means, the number of loans that you have, how much money you make, how many times you've defaulted, how many times you've been late, the sort of things that make up credit history. And the output of the learning algorithm is whether you should lend money or not. So you're a bank and you're trying to determine whether, given a credit history, I should lend this person money. That's question 1. Is that classification or is that regression? Question 2, you take as input a picture like the examples that we've given before. And the output of your learning system is going to be whether this person is of high school age, college age, or grad student age. The third question is very similar. The input is, again, a picture, and the output is a guess of the actual age of that person, 17, 24, 23 and a half, whatever. So take a moment and try to decide whether these are classification tasks or regression tasks. And so now let's give the explanation for the quiz.
All right, so let's see what happened here. So what you're saying is in some cases the inputs are discrete or continuous or complicated. In other cases, the outputs can be discrete or continuous or complicated. But I think what you're saying is that what matters to determine if something's classification or regression is whether the output is from a discrete small set or whether it's some continuous quantity. Is that right?
Right, that's exactly right. What the difference between a classification task or a regression task is not about the input, it's about the output. If the output is continuous, then it's regression, and if the output is small discrete set or discrete set, then it is a classification task. So with that in mind, what do you think is the answer to the first one, Michael?
So lend money. If it was something like predicting a credit score, that seems like a more continuous quantity. But this is just a yes/no, so that's a discrete class. So I'm going to go with classification.
That is correct. It is classification, and the short answer is because it's a binary task. True, false, yes, no, lend money or don't lend money.
Got it.
So it's a simple classification task. Okay, with that in mind, what about number 2?
All right, so number 2, it's trying to judge something about where they fall on a scale, high school, college, or grad student. But all that the system is being asked to do is put them in one of those 3 categories, and these categories are like classes, so it's classification.
That is also exactly right, classification. We moved from binary to trinary in this case, but the important thing is that it's discrete. So it doesn't matter if it's high school, college, grad, professor, elementary school, any number of other ways we might decide where your status of matriculation is. It is a small discrete set. So with that in mind, what about number 3?
All right, so the input is the same in this case, and the output is kind of the same, except there's certainly more categories because there's more possible ages than just those 3. But when you gave the example, you did explicitly say that ages can be fractional, like 22.3. So that definitely makes me think that it's continuous, so it should be regression.
Right. I think that is exactly the right thing. You have a continuous output. Now, I do want to point something out, that while the right answer is regression, a lot of people might have decided that the answer was classification. So what's an argument? If I told you, in fact, the answer was classification, what would be your argument for why that would be?
Well, I guess...
Can you think of one?
I guess, if you think about ages as being discrete, you just say, you can be 1 or 2 or 3 or, whatever, up to 130, say. But there's just that set. There isn't really, usually we don't talk about fractional ages. So it seems like you could think of it as a set of classes.
Right. So let's imagine, how old do people, so let's imagine we only cared about years. So you're either 1 or 2 or 3 or 4 or 5. Or maybe you can be 1.5 and 2.5 and 3.5, but whatever. It's not all possible real number values. And we know that people don't live beyond, say, 250. Well, in that case, you've got a very large discrete set, but it's still discrete. Doesn't matter whether there's 2 things in your set, 3 things in your set, or in this case, 250 things in your set, it's still discrete. So whether it's regression or classification depends upon exactly how you define your output, and these things become important. I'm going to argue that in practice, if you were going to set up this problem, the easiest way to do it would be to think about it as a real number, and you would predict something like 23.7. And so it's going to end up being a regression task. And we might maybe think about that a little bit more as we move along. So either answer would be acceptable depending upon what your explanation of exactly what the output was. You buy that?
That makes sense.
Excellent. Okay. All right, let's move beyond the quiz and start thinking about exactly what it means to define a classification problem, and then later what it means to define a regression problem. Okay, so classification learning. Before we get into the details of that, I want to define a couple of terms because we're going to be throwing these terms out all throughout the lessons, and I want to make certain that we're all on the same page and we mean the same thing. We'll be returning to this again and again and again. So the first term I want to introduce is the notion of instances. So instances, or another way of thinking about them, is input. Those are vectors of value, of attributes that define whatever your input space is. So they can be pictures and all the pixels that make up pictures, like we've been doing so far before. They can be credit score examples, like how much money I make or how much money Michael makes. How much money I wish I made, and so on and so forth. So whatever your input value is, whatever it is you're using to describe the input, whether it's pixels or it's discrete values, those are your instances, the set of things that you're looking at. So you have instances, that's the set of inputs that you have. And then what we're trying to find is some kind of function And that is the concept that we care about. And this function actually maps inputs to outputs. So it takes the instances and maps them, in this case, to some kind of output such as true or false. This is the category of things that we're worried about. And for most of the conversation that we're going to be having, we're going to be thinking about binary classification, just true and false. But the truth is this would work whether there were 3 outputs, as we did with high school, college, or grad school, or whether there were 250 as we were contemplating for ages. But the main thing here is the concept is the function that we care about that's going to map pictures, for example, to true or false.
So okay, so I get the use of the word instance, right? An instance is just like a single thing that's out there.
Mm-hmm.
But I have an intuitive notion of what a concept is. How does that relate to this more formal notion? Like, can we connect this to kind of the intuitive notion of what a concept is?
I guess so. A concept, I don't know. How would you want to put that? So a concept is something that, we're talking about it as a notion of a function. So what it means formally is that you have some input, like a picture, and it immediately maps anything in that input space to some particular defined output space, like true or false, or male or female, or creditworthy or not. Intuitively, a concept is an idea that describes a set of things. Right? So we can talk about maleness or femaleness. We could talk about short and tall. We can talk about college students and grad students. And so the concept is the notion of what creditworthiness is, what a male is, what a college student is.
Okay, I think I see that. So essentially, if you want to think of tallness, the concept of tallness, one way to define it is to say, well, in general, if you give me something, I can tell you whether or not it's tall. So it's going to map those somethings to, am I tall or not, true or false?
Right, exactly. And so really, when you think about any concept, and when we talk about this in general in AI, right, a concept is effectively a set of things that are a part of that concept. So you can have a concept of a car, and if I gave you cars, you would say these things are in it. And if I gave you non-cars, you would say they are not. And so a concept is, therefore, by definition, a mapping between objects in the world and membership in a set, which makes it a function.
Okay, that makes sense.
Okay. So with that notion of a concept as functions or as mappings from objects to membership in a set, we have a particular target concept. And the only difference between a target concept and the general notion of concept is that the target concept is the thing we're trying to find. It's the actual answer. Right? So a function that determines whether something is a car or not, or male or not, is the target concept. Now, this is actually important, right? Because we could say that we have this notion in our head of things that are cars or things that are males or people who are creditworthy, but unless we actually have it written down somewhere, we don't know whether it's right or wrong. So there is some target concept we're trying to get of all the concepts that might map pictures of people to true and false.
Okay, so if you're trying to teach me what tallness is, so you have this kind of concept in mind of these things are tall and these things are not tall, so you're going to have to somehow convey that to me. So how are you going to teach me?
So that's exactly that's what comes up with the rest of these things that we're defining here. So let me tell you what the next 4 things are, and then you can tell me whether that answers your question.
Got it.
How about that? Okay. So we've got a notion of instances, input. We've got a notion of concepts, which take input and maps them to some kind of output. And there's some target concept, some specific function, some particular idea that we're trying to find and we're trying to represent. But out of what? So that's where the hypothesis comes in. In fact, I think it's better to say hypothesis class. So that's the set of all concepts that you're willing to entertain. So it's all the functions I'm willing to think about.
So why wouldn't it just be all possible functions?
It could be all possible functions, and that's a perfectly reasonable hypothesis class. The problem with that is that if it's all possible functions, it may be very, very hard for you to figure out which function is the right one given finite data. So when we actually go over decision trees next, I think it'll be kind of clear why you need to pick a specific hypothesis class to think about.
Okay.
So let's return to that in a little bit, but it's an excellent question. So conceptually in the back of your head until we come to specific examples, you can think of hypothesis class as simply being all possible functions in the world. On the other hand, even so far, just with classification learning, we already know that we're restricting ourselves to a subset of all possible functions in the world. because all possible functions in the world includes things like x squared, and that's regression. And we've already said we're not doing regression, we're doing classification. So already the hypothesis class is all functions we care about, and maybe it's all classification functions. So we've already picked a subset. So we've got all these instances, we've got all these concepts, we want to find a particular concept, and we've got this set of functions that we're willing to look at. So how are we going to determine what the right answer is? So if we try to answer Michael's question, the way that we do that in machine learning is with a sample, or another name for it, which I prefer, is a training set. So what's a training set? Well, a training set is a set of all of our inputs, like pictures of people, paired with a label, which is the correct output. So in this case, yes, this person is credit worthy. Versus another example.
You can tell I'm credit worthy based on my curly hair.
Purely on the hair. Versus someone who has no curly hair and therefore is obviously not credit worthy. And if you give bunches of examples of input and output pairs, that's a training set. And that's what's going to be the basis for you figuring out what is the correct concept or function.
I see. So instead of just telling me what tall means, you're going to give me lots of examples of this is tall, this is not tall, this is tall, this is tall, this is tall, this is not tall. And that's the way that you're explaining what the target concept is.
Right. So if you want to think about this in the real world, it's as if we're walking down the street and I'm pointing out cars to you and non-cars to you, rather than trying to give you a dictionary that defines exactly what a car is. And that is fundamentally inductive learning, as we talked about before. Lots and lots of examples, lots of labels. Now I have to generalize beyond that. So last two things that we talk about, last two terms I want to introduce are candidate and testing set. So what's a candidate? Well, a candidate is just simply a concept that you think might be the target concept. So, for example, I might have, right now, you already did this, where you said, oh, okay, I see. Clearly, I'm credit worthy because I have curly hair. So you've effectively asserted a particular function that looks for curly hair and says, if there's curly hair there, the person's credit worthy, which is certainly how I think about it. And people who are not curly hair, who do not have curly hair, are in fact not credit worthy. So that's your target concept. And so then the question is, given that you have a bunch of examples and you have a particular candidate or a candidate concept, how do you know whether you're right or wrong? How do you know whether it's a good candidate or not? And that's where the testing set comes in. So a testing set looks just like a training set. So here, our training set will have pictures and whether someone turns out to be credit worthy or not. And I will take your candidate concept and I will determine whether it does a good job or not by looking at the testing set. So in this case, because you decided curly hair matters, I've given you two examples from a training set, both of which have curly hair, but only one of which is deemed credit worthy, which means your target concept is probably not right.
So to do that test, I guess you can go through all the pictures in the testing set, apply the candidate concept to see whether it says true or false, and then compare that to what the testing set actually says the answer is.
Right, and that'll give you an error. So by the way, the true target concept is whether you smile or not.
Oh, that does make somebody credit worthy.
It does in my world, or at least I wish it did in my world. Okay, so by the way, an important point is that the training set and the testing set should not be the same. If you learn from your training set and I test you only on your training set, then that's considered cheating in the machine learning world, because then you haven't really shown the ability to generalize. So typically we want the training set to include lots of examples that you don't the testing set, to include lots of examples that you don't see in your training set. And that is proof that you're able to generalize.
I see. So that makes intuitive sense, right? So like if you're a teacher and you're telling me, you give me a bunch of facts and then you test me exactly that bunch of facts, I don't have to have understood them. I just can regurgitate them back. If you really want to see if I got the right concept, you have to see whether or not I can apply that concept in new examples.
Yes, which is exactly why our final exams are written the way that they're written. Because you can argue that I've learned something by doing memorization, but the truth is you haven't. You just memorized. Here, you have to do generalization. As you remember from our last discussion, generalization is the whole point of machine learning. All right, so we've defined our terms. We know what it takes to do at least supervised learning. And so now I want to do a specific algorithm and a specific representation that allows us to solve the problem of going from instances to actual concepts. So what we're going to talk about next are decision trees. And I think the best way to introduce decision trees is through an example. So here's the very simple example I want you to think about for a while. You're on a date with someone, and you come to a restaurant, and you're going to try to decide whether to enter the restaurant or not. So your input, your instances, are going to be features about the restaurant. And we'll talk a little bit about what those features might be. And the output is whether you should enter or not. Okay, so it's a very simple, straightforward problem, but there are a lot of details here that we have to figure out.
It's a classification problem.
It's clearly a classification problem because the output is yes, we should enter, or no, we should move on to the next restaurant. So in fact, it's not just a classification problem, it's those binary classification problems that I said that we'd almost exclusively be thinking about for the next few minutes. Okay, so you understand the problem setup?
Yes, though I'm not sure exactly what the pieces of the input are.
Right, so that's actually the right next question to ask. We have to actually be specific now about a representation. Before I was drawing squiggly little lines and you could imagine what they were, but now since we're really going to go through an example, we need to be clear about what does it mean to be standing in front of a restaurant. So let's try to figure out how we would represent that and how we would define that. We're talking about you're standing in front of a restaurant or eatery because I can't seem to reliably spell restaurant, and we're going to try to figure out whether we're going to go in or not. But what do we have to describe our eatery? What do we have? What are our attributes? What are the instances actually made of? So or another way of putting it is, what are the features that we need to pay attention to that are going to help us to determine whether we should, yes, enter into the restaurant, or no, move on to the next restaurant? So any ideas, Michael?
Sure. I guess there's like the type of restaurant.
Okay.
So is it tall or short, and is it a good credit risk? Oh wait, no, I know, like Italian versus French versus Vietnamese.
So let's call that the type. So it could be Italian, it could be French, it could be Thai, it could be American. They're American restaurants, right?
Sure.
Greek, it can be Armenian, it can be any kind of restaurant you want to. Okay, good. So that's something that probably matters because maybe you don't like Italian food, or maybe you really are in the mood for Thai. Sounds perfect. Okay, anything else?
Sure. How about whether it smells good?
Yeah, I like cleanliness. Or you know what? Let's be nice to our eateries and let's say atmosphere.
Right, because if there's no atmosphere, then it's going to be really hard to breathe.
That's exactly right. So is it fancy? Is it a hole in the wall? Which I'm going to spell H-I-W. Is it a hole in the wall? Those sorts of things.
Casual, I guess, is another category.
Casual. And so on and so forth. You can imagine lots of things like that, but these things might matter to you in your date. Okay, so we know the type of restaurant that we have. We know whether it's fancy, whether it's casual, whether it's a hole in the wall. Some of the best food I've ever had are in well-known hole in the walls. Those sorts of things. Anything else you can think of?
Sure. Sometimes I might use something like looking inside and seeing whether there's people in there, whether they look like they're having a good time.
Right. So that's an important thing. So let's just say if it's occupied. Now, why might that matter in reality? Well, it matters because if it's completely full and you may have to wait for a very long time, you might not want to go in. On the other hand, if you're looking at a restaurant you've never heard of and there's only 2 people in it and it's Friday at 7 p.m., maybe that says something about something. So maybe you want it to be quiet. Those sorts of things might matter. Okay, so we've got type, we've got atmosphere, we've got occupied. Anything else you can think of?
I have been out of the dating market for a while, but I guess I could imagine how hard I am trying to work to impress my date.
Ah, perfect. So do you have a hot date or not? Or this is someone you really, really, really want to impress, and so maybe it matters then. It's even more important whether it's a fancy restaurant or a hole in the wall, or whether it's French, or whether it's an American restaurant. That makes sense? I think that makes sense. Notice, by the way, that the first 2 sets that we have multiple possible categories here. So they could be Italian, French, Thai, American, so on and so forth. Atmosphere is something that can have many, many possible values. But the last 2 things that we talked about were all binary. Either it's occupied or it's not, yes or no, or you have a hot date or you don't. And I think we could go on like this for a long time. But let's try to move on to maybe a couple of other features and then try to actually figure out how we might solve this. All right, so Michael, Last set of features that let's come up with three or four more features and then move on.
Sure.
So come up with a
All
couple.
right. So sometimes I'll look at the menu that's posted outside and I'll see if how pricey it is.
Okay. So cost. Right. So cost can be represented as discrete input. By the way, it could also be represented as an actual number. Right. We could say, look, it's cheap, it's moderately expensive, it's really expensive. Or you could have a number, which is the average cost of an entree. And it doesn't really matter for what we're talking about now, but just some way of representing cost. Okay, let's give me one or two more features, but I want you to give me some features that don't have anything to do with the restaurant itself, but might still be important. Because, by the way, hot date probably doesn't have anything to do with the restaurant itself. So even though we've been talking about features of the restaurant, we've actually been picking up at least one feature that doesn't have anything to do directly with the restaurant itself.
So whether I'm hungry?
I like that. Here's another one. What's the weather like? Is it raining outside?
Which is a different sense of atmosphere.
Right. Because if it's raining outside, maybe it's not your favorite choice, but you don't want to walk anymore. Okay, so we have a ton of features here. We've gone through a few of them. Notice that some of them specifically have to do with the restaurant, and some of them have to do with things that are external to the restaurant itself, but you can imagine that they're all important, or possibly important, to whether you should enter into the restaurant or not. Agreed?
Agreed.
Right, and there's a bunch of features you could imagine coming up with that probably have nothing to do with whether you should enter into the restaurant or not, like how many cars are currently parked across the country. Probably doesn't have an impact on whether you're going to enter into a specific restaurant or not. Okay, so we have a whole bunch of features, and right now we're sticking with features we think might be relevant, and we're going to use those to make some kind of decision. So that gets us to decision trees. So the first thing that we want to do is we want to separate out what a decision tree is from the algorithm that you might use to build a decision tree. So the first thing we want to think about is the fact that a decision tree is a specific representation. And then only after we understand that representation and go through an example will we start thinking about an algorithm for finding or building a decision tree. Okay? Are you with me?
Yeah.
Excellent. Okay, so a decision tree is a very simple thing. Well, you might be surprised to know it's a tree, the first part of it, and it looks kind of like this. So what I've drawn for you is an example sample generic decision tree. And what you'll see are three parts to it. The first thing you'll see is a circle. These are called nodes, and these are, in fact, decision nodes. So what you do here is you pick a particular attribute, and you ask a question about it. The answer to that question, which is its value, or what the edges represent in your tree. Okay, so we have these nodes, which represent attributes, and we have edges, which represent values. So let's be specific about what that means. So here's a particular attribute we might pick for this top node here. Let's call it hungry. That was one of the features that Michael came up with. Am I hungry or not? And there's only two possible answers for that. Yes, I'm hungry, true, or false, I am not hungry. And each of these nodes represents some attribute, and the edges represent the answers for specific values. So it's as if I'm making a bunch of decisions by asking a series of questions. Am I hungry? And if the answer is yes, I am hungry, then I go and I ask a different question, like, is it rainy outside? And maybe it is rainy, and maybe it's not rainy. And let's say if it isn't rainy, then I want to make a decision. And so these square boxes here are the actual output. Okay, so it's hungry. So you're hungry, yes, and it's not raining. So what do? So let's just say you go in. True, I go in. So when it's I'm hungry, but it's not raining, I go in.
And that true is answering a different question. It's not in the nodes, I guess. So in the leaves, the T and F mean something different.
That's right. It's exactly right. The leaves, the little boxes, the leaves of your decision tree is your answer. What's on the edges are the possible values that your attribute can take on. So in fact, let's make that clear by picking another possible attribute. You can imagine that if I'm not hungry, what's going to matter a lot now is, say, the type of restaurant, right? of which we said there were many, many types of restaurants. So, Thai, I forget what other ones we came up with, Italian, and, something
French
else.
fries.
And French fries. So if I'm not hungry, then what matters a lot more is the type of restaurant, and so I'll move down this path instead and start asking other questions. But ultimately, no matter what this decision tree allows me to do is to ask a series of questions, and depending upon those answers, move down the tree until eventually I have some particular output answer. Yes, I go in the restaurant, or no, I do not.
Okay, this is still seeming a little bit abstract to me. Can we maybe work through a very concrete example?
Yeah, I think that makes a lot of sense.
Let's do a quiz.
Okay, let's do a quiz. Okay, so we've now seen an abstract example of a decision tree, so let's make certain that we understand it with a concrete example. So to your right is a specific decision tree that looks at some of the features that we talked about, whether you are occupied or not, whether the restaurant is occupied or not, what type of restaurant it is. Your choices are pizza, Thai, or other. And whether the people inside look happy or not. And the possible outputs are, again, binary. Either you don't go or you do go into the restaurant. On your left is a table which has 6 of the features that we've talked about, whether the restaurant is occupied or not, the type of restaurant, whether it's rainy outside or not, whether you're hungry or not, whether you're on a hot date, and whether the people inside look happy, and some values for each of those. And what we would like for you to do is to tell us what the output of this decision tree would be in each case.
All right, so the decision tree here is it's a classifier, but we had another name. Oh, it's a concept.
Yes.
All right, and each row of this is a different time that we're stopping at a restaurant, and the little values there summarize what is true about this particular situation. And you're saying we need to then trace through the decision tree and figure out what class is. Okay, yeah, that's what you said. Okay, I'm ready.
All right, perfect. Okay, that's the quiz. Go. You've got your answers, so let me tell you what we think the answers are. Now, the nice thing about a decision tree, sort of conceptually and intuitively, is that it really is asking a series of questions. So we can simply look at these rows over here and the values that our features have, and we can just follow down the path of the tree. So in the first case, we have true. We have true for occupied, which means we want to go down the right side of the tree and check on the type. So in the first case, the type is pizza. And so we go down the first branch, and that means we do not go down the tree. So the output is no go.
So, okay, so now I got a different answer. So I looked at this and I said, happiness is true, and the bottom box says happiness true, you go.
Right, so you got what I'm going to tell you is the wrong answer by going from the bottom of the tree up. The way decision trees work is you always start at the root of the tree. That is the very top of the tree. And you ask the questions in that order.
It just seems like it would be faster to start at the bottom.
Yeah, but then you would never look at anything else in the tree.
Ah, good point. All right, so
right? If you start at the bottom, you can't go up.
All right. So, okay, so let me see if I get this straight. So I'll do this second instance. The second instance, you say that we need to start at the top of the tree where it says occupied. And so now I look at the instance, and the instance says that it's false for occupied. So we go down that left branch, and we hit no-go. Oh, wait, but now I haven't looked at any of the other nodes.
And you don't have to look at any of the other nodes because it turns out that if it's not occupied, you just don't go into a restaurant. So you're the type of person who doesn't like to be the only person in a restaurant.
Got it. All right. So that's a no-go.
So that's a no-go. That's an important point, Michael. Actually, you might also notice that this whole tree, even if you look at every single feature in the tree, only has 3 of the attributes. It only looks at occupied, type, and happiness.
I see. So hot date is sort of irrelevant, which is good because in this case, it's not really changing from instance to instance anyway.
True, and neither is hungry, you might notice.
Oh, I am kind of hungry.
Although I'm always hungry. Although rainy does in fact change a little bit here and there. But apparently it doesn't matter.
I see.
Because you always take an umbrella.
Got it.
Okay, so let's quickly do the other 3 and see if we come to the same conclusion.
All right, well, all the instances that have occupied false, we know those are no-go right away.
Oh, good point.
So we can do it kind of out of order. and the other ones are both occupied. One is tie and one is other. For the tie one, we go. And for the other one, oh, I see. For the other one, we have to look at whether there's happiness or not. And in this instance, happiness is true. So we go down the right branch and we go.
And we go. Exactly it. So we notice that hot date doesn't matter, hungry doesn't matter, and rainy doesn't matter. The only thing that matters are whether you're occupied, what type of restaurant you're at, and whether you're happy or not, or whether the patrons in the restaurant are happy or not. But here's the other thing about this. It's not just about the features. Let's tie it back into the other things that we mentioned in the beginning. This, in our case, this table actually represents our testing set. It's the thing that we're going to look at to determine whether we were right or wrong. These are the examples that we're going to do to see whether we generalize or not. And this particular tree here is our candidate concept. So there are lots and lots and lots of other trees that we might have used. We might have used a tree that also asked questions about whether it was rainy or not, or asked questions about whether you were on a hot date or not, but we didn't. We picked a specific tree that had only these three features and only asked in this particular way. So what we're going to talk about next is how we might decide whether to choose this tree over any of the other possible number of trees that we might have chosen instead.
All right, so we understand at this point how to use these decision trees, but this is a class about machine learning, right? So we need to figure out how to make those decision trees happen as a result of processing a set of training data. So it's not clear to me how we're going to make that leap.
Let's see if we can figure it out together. So I'm going to play a game with you, Michael, and if we do the game well, then I think we'll have an idea of what a good algorithm might be for actually building a decision tree. So we're going to play 20 questions. You're familiar with 20 questions?
Right. That's the game where I'm allowed to ask yes/no questions to try to guess something that you're thinking of. And if I take more than 20 of them, then I lose.
Right. Okay. So here's what I'm going to do. I'm going to think of a thing, and you ask me questions, and I'm going to answer them, and we'll see if you can guess what thing I'm thinking about. Okay. I've got something in my head.
First question, the typical first question, is it animal, vegetable, or mineral? But that doesn't seem like a yes/no question. So is it an animal or like a living creature?
The answer is yes.
All right. Is it a person?
Is it a person? The answer is yes.
Is it a famous person?
Oh. Is it a famous person? Well, that's a deep philosophical question, but I'm going to say yes.
Is it a famous person that we both know like directly?
Oh, who we both personally know directly? I do not
Yeah.
believe so. So the answer is no.
Is it a living person?
Living person? No.
So it's a dead famous person. Is the person famous for, say, being in the music industry?
The answer is yes.
Did this person live during the 20th century?
The answer is yes.
Is the genre of music that the person was associated with, say, hip-hop or rap?
No.
Is the person a singer?
Singer? Yes.
Male or female? Is the person female?
Person female? No. That's 10 questions, Michael.
Yes, the clock is ticking down, but I feel like I have narrowed it down quite a bit at this point. Did the person die since you've become a professor? So say in the last, how long have you been a professor?
Forever, it sounds like. Feels like. Let's see. Recent death. And I'm going to say the answer is yes.
Is the person's name Michael?
The answer is yes.
All right. I think I'm on to it. Is it Michael Jackson?
No.
Woohoo!
Of course it's Michael Jackson.
All right. Thriller.
Yes, Michael Jackson is the answer.
All right, so that was very fun, and I'm very glad that I was able to solve it. But it's not clear to me how this is going to give us an algorithm for building decision trees.
Okay, so let's think about that for a second. So you asked a bunch of questions, and you asked them in a particular order, right? So here's a question I have for you. Why was the first question you asked me whether it was an animal or not?
Well, It seemed like I needed some way of narrowing down the space. And so I wanted to get as much information out of that question as I could to try to make progress towards figuring out who actually was.
Right. So animal was the first question, and it was because it narrowed things down. So your goal in asking questions was to narrow the possibilities, right?
Sure. Right, because I only have 20 questions and then I'm out of it. So if I asked questions like, you know, if I had started with, is it someone named Michael, that would have been really bizarre.
Right. And if the answer was no, it's not clear that it would tell you anything at all. So actually, that's an interesting point. You started with animal. You could have started with Michael. And if I had said yes, that would have told you something. But if I had said no, it wouldn't have told you hardly anything at all. Right? So animal is a better attribute or feature to ask about than Michael as a first question. You agree with that?
Yeah, because it could have been like a stapler or something like that, and then the Michael question would have been pretty silly.
Exactly. So what about person? So first you asked about animal, then you asked about person. Why person?
Right, because again, it seemed like of the space of possibilities that I could think of, person would help kind of again narrow things down. That if it was the answer was yes, I would be able to focus there. If the answer was no, I could focus someplace else.
Exactly. And so I think, in fact, we could have a general statement here that each one of these questions, person, famous, do we know this person personally, so on and so forth, all make sense because they further narrow down the possibilities. And that bit about further is important because it implies that the usefulness of a question depends upon the answers that you've gotten to previous questions. So even though Michael is not a particularly good first question to ask, it's a perfectly reasonable 12th question to ask, or however far down it is, given that you already know this is an animal, a person, a famous person we don't know personally, who's not living, was into music, et cetera, et cetera, et cetera. Okay, that make sense?
Yeah.
Okay, so I think then we have the hints of an algorithm. So let's try to write down that algorithm and see if it matches with our intuition. Okay, so inspired by 20 questions, let's try to write down exactly what it is that you did in going through your 20 questions to get your answer to discover Michael Jackson was the person I was thinking about. So what was the very first thing you did?
I tried to imagine a bunch of possible answers that you could could have in mind, and I tried to think of a question that would help separate them into two roughly equal chunks.
Okay, so what's a way of putting that in the language that we've been using for supervised learning and classification so far?
Oh, I see. So if I had known in advance, here's 200 things that you might ask me about, and what their attribute values are. What would be a question that would split that set in half? Right. So if instead of just imagining a bunch of things, if I actually had a list, which I do in the case of a training set.
All right, so the first thing you did is you picked the best attributes that you could think of. And by the way, you said something very particular here. You've actually defined what best is. You said that best is the same thing as splitting things roughly in half. So let's revisit that in a moment. Okay, so the first thing you did is you picked the best attribute. You asked a question about it. And then, depending upon the answer, you went and picked another attribute, right? Does that seem fair?
Yeah.
Okay. So if we think about decision trees, a way of talking about that is that you follow the path of the answer. And then lather, rinse, and repeat. You went back and picked the best attribute, asked a question, followed the answer path, so on, and you kept doing that until what?
Until I narrowed the space of possibilities to, in this case, just one item.
Right, so until you got to the answer, right? And that is an algorithm. So you pick the best attribute, and you actually define what best attribute was. You wanted to pick one that would somehow eliminate at least half of the things that you might worry about and keep the other half in play. You asked the specific question, you follow the path to that, and then you went back and you picked another attribute, and so on and so forth until you got an answer that you wanted to. That's an algorithm, and that's an algorithm that we might use to actually build a decision tree. And the only difference between what you did And what you would do with learning a decision tree is that since you don't know in advance what the answer actually is going to be, because you don't know what specific object I might be thinking of, you have to actually follow all possible paths at each time and think of all possible best next attributes until you completely can answer any question. Does that make sense?
I see. So, right. So instead of just playing the game interactively, I kind of imagine all possible ways it could go and build that whole flowchart, that whole tree.
Right. So let's see if we can do that with some pictures. And I actually want to decide whether I really believe your definition of best. Okay?
Sure.
All right, so let's do that. All right, so let's take a moment to have a quiz where we really delve deeply into what it means to have a best attribute. So something Michael and I have been throwing around that term. Let's see if we can define it a little bit more crisply. So what you have in front of you are 3 different attributes that we might apply in our decision tree for sorting out our instances. So at the top of the screen, what you have is you have a cloud of instances. They're labeled either with red X or a green O, and that represents the label. So that means that they're a part of our training set. So this is what we're using to build and to learn our decision tree. So in the first case, you have the set of instances being sorted into 2 piles. There's some X's and some O's on the left and some X's and some O's on the right. In the second case, you have that same set of data being sorted so that all of it goes to the left and none of it goes to the right. And in the third case, you have that same set of data that's sorted so that a bunch of the X's end up on the left and a bunch of the O's end up on the right. What I want you to do is to rank each one, where 1 is the best and 3 is the least best attribute to choose. Go. Okay, Michael, so are you ready to give me a ranking?
Yes. Yes, I think I am.
Okay, well, give me a ranking then.
So did you say 1 was the best?
1 is the best and 3 is the least best.
All right. So I am really excited about the third cloud structure, the third attribute to be split on, because what it does is it takes all our X's and O's that need to have different labels and it puts them into 2 different buckets, one where they all get to be red X's and the other one where they all get to be green O's. So I would say the far right one is ranked number 1.
I would agree with you. And in fact, I would say that, we're done.
Yeah, it's perfect.
It is perfect. Agreed. 1 is perfect. Or 3 is perfect in this case, because I gave it a 1.
All right. So then the worst one, I think, is also easy to pick, because if you look at the middle attribute, the attribute that's shown in the middle, we take all the data and we put it all on the left. So we really have just kicked the can down the road a little bit. There's nothing that this attribute splitting has done. So I would call that the worst possible thing you could do, which is basically to do nothing.
No, I think that's right. And in fact, it really is doing nothing.
Right.
Okay. So what about the first attribute?
So I'm going to put that at, if the first one is too hot and the middle one is too cold, I would say this one is, wait, no. I was going down the Goldilocks path. So this one is sort of in between in that it splits things, so you have smaller sets of data to deal with, but it actually hasn't really improved our ability to tell the reds and the greens apart. So in fact, I'd almost want to put this as 3 also, but I'll put it as 2.
Okay. Yeah, I think an argument could be made for making it 3. An argument could be made for making it 2. Your point is actually pretty good, right? We had sort of 8 red things and 8 green things up here, and the kind of distribution between them, sort of half red X's, half green O's, we have the same distribution after we go through this attribute here. So it does some splitting, but you still end up with half red, half green, half X, half O. So that's not a lot of help, but it's certainly better than doing absolutely nothing.
Well, is it though? I mean, it seems like it could also be the case that what we've done is we've added an attribute that we're now splitting on that has provided no valuable information and therefore can only contribute to overfitting.
That's a good point. That's a good point. So do you want to change your answer to 3?
I don't know. What did you want the answer to be? I mean, it seems to me that the first and the second one are just plain bad.
They are just plain bad. The question is whether one is more bad than the other.
I don't know. I don't know how to judge.
Well, I'll tell you, I would accept either a 2 or a 3 as an answer here. I think you can make an argument either way, and I think you actually made both arguments.
That's very nice of you. Thank you.
No, you're very welcome. So this is perfect. This is the House of Representatives, and this is the Senate.
What do you mean? Oh.
So there you go. Okay.
I'm not exactly sure what you mean, but it
Oh, I think
seems
you
somehow
know what I
denigrating to our political system.
It is not at all denigrating. It is. I would call it incisive political satire. Okay, so Michael, for the last 15 minutes or so, we've been talking about decision trees, sort of in the abstract, without saying too much about the kinds of functions they can actually represent. So for the next few minutes or so, I want to talk a little bit about not just decision trees in the abstract, but exactly how expressive they can be. Is that okay?
Yeah, I think that would be really helpful.
I think so too. So in fact, I want to look at a set of functions, and in particular, I'm interested in looking at Boolean functions.
Boolean.
So what's your favorite simple Boolean function?
Implication.
What's your other favorite simple Boolean function?
Well, I like nor.
Right. So what I just heard you say is you like and. So let's do that one.
Oh, that's great. That is my favorite.
All right. So in fact, let's do very simple and. So how does and work, right? So you've got two attributes, let's say A and B. And this expression A and B is true when?
When A and B are true, when they're both true at the same time.
Right, exactly. So how would you build a decision tree, given that there are only two attributes, A and B, to represent that function?
Okay, so I'd have a node that's A and B, and if
Nope,
that's
you're not allowed to do that.
oh,
Every node can have at most one attribute.
all right. Well, let's put A in an attribute.
Okay, so here's a little node. Let's call it A.
Okay.
Now what?
And well, I mean, for it to be a node, it needs to have the little two branchy things, true and false.
Okay. All right. So how about true on the left and false on the right?
Sure, as long as you label them. So, all right. So then if A is true, okay, I don't know, but if A is false, then we know that A and B must be false. Doesn't matter what B is. So we can just put
That's
a leaf
correct.
under the F.
All right, I like that.
Okay.
What about when A is true?
What is that, an F?
That is an F, and that is a minus sign.
Oh, a
for
minus sign.
false.
I get it. Okay, I thought you were just not done drawing the F yet. Good. All right. So, okay, the true side, then I don't think we know. So I think we need to split on B also.
Okay.
So put a little B under there.
All right, done.
All right, and then true, false, split on B. All right, and so now we've got these two cases. So if B is false, then again, it doesn't matter what A was, but A turns out to be true, but it's still it should be a minus sign underneath that.
Okay.
So it's not, A and B is not true. But if A is true and B is true, then A and B is true. So there should be a plus sign on the left.
That's exactly right.
Woo.
So clearly decision trees, proof by we just drew it here, can represent the Boolean function and.
Sure. At least on
Right.
two
Now
inputs.
you said something interesting, Michael. You said it doesn't matter what A is if B is false. So what would happen if I switch A and B around?
That's the same. So if B, okay, so in the beginning we say if B is false, it's false. If B is true, we check A. If A is false, then it's false. But if A is true, then it's true. So it actually still represents exactly the same function, A and B. Oh, because A and B is collaborative. No, commutative. Yes? No? Hello?
It's one of those things. It's commutative.
Commutative.
As opposed to associative?
As opposed to what?
Associative.
Well, I mean, it's that too. But I mean, it's the reason that you could just switch those two things and it didn't make a difference is because they play the same role in the function.
That's true. And in terms of the representation of decision trees, it doesn't really matter which attributes you pick or the order in which you do them. You might get a better tree or a worse tree, a longer tree or a shorter tree. But for something simple like two-valued and, it really just doesn't matter.
Okay.
Kind of neat, huh?
Yeah.
Okay, so we can do A and B. So let's pick another function. What's your other favorite Boolean function of two variables?
Well, if we're doing two attributes, or is the other really nice one.
I like or. So let's see. Do you think now that we've shown that we can do A and B, could we do A or B?
I feel like we can do A or B because there's that nice De Morgan's law relationship between them. But let's just, how about this? Can you erase the tags at the bottom?
Like that?
Oh, yeah, but that's not going to work, is it? So if B and A are both true, so the left branch, then the leaf should be plus.
Yes.
And if B is true and A is false, then the tag should be plus.
Yes.
And if B is false, I want to say false, but we don't know because A could be true, and A or B is true if either of the two of them are true.
Okay, so maybe the mistake here is just trying to use exactly the same thing. So let's just erase it
All right.
and start from scratch. So what would you do starting from scratch?
I'd split on B again.
Okay,
True, false, or false, true. True, false.
true, false.
All right, and now if B is true, we know that A or B is true. So we can put a plus under the left side.
Right.
But if B is false, then we need to split on A.
Okay,
And if A is true, then we're golden. We get the or is true. And if A is false, then it is false.
very good. And that represents A or B.
That represents the function, the logical function A or B. Yeah.
Right. And what happens if I swap A and B around? Does it still work?
I mean, since they're collaborative or commutative, I want to say it shouldn't make a difference, but let's just double check that. So if A is true, then the output's true. If A is false and B is true, then the output is true. And if A and B are both false, then the answer is false. Yeah, totally.
Excellent. And, you know, if I hadn't erased it, you would see that the two trees actually looked very, very much alike.
They're sort of
We just swapped
mirror-ish of
around.
each other.
Yeah, exactly. They're mirrors of one another. Okay, let's pick one more Boolean function to do. What function am I thinking of?
XOR is always good.
Let's do XOR. So what does XOR mean? Remind me.
Okay, XOR is exclusive OR, which means it's true if A is true or B is true, but not if they're both true. So it has elements of both OR and in it.
Right.
And I think of XOR usually when I'm like playing with light switches in my house. If I have a light that's activated by two different light switches, it's usually an XOR function. If one is up, the light's on. If the other one's up, the light's on. But if they're both up, the light goes back off.
Right. The other thing, when I think of XOR is when people say OR. Most of the time when people say OR, when they're talking, they mean XOR.
Really?
Yeah, so a lot of times when people say OR in English, they really mean XOR. They say, well, do you want to go to the movies or do you want to go swimming? Do you want to eat chicken or do you want to eat fish? And really they're saying either or.
I see. You want one or the other, but you can't have chicken and fish or go swimming and the movies.
No, those things are not possible to do together.
Got it. Okay.
All right, so how would you do XOR? We still
I
have
would
our two
start with
attributes A and B.
OR, because it's a lot like OR.
So what would you want to do?
Okay, so to do XOR, we can split on A,
Okay.
and there's a true branch and a false branch. And what happened with and OR at this point is there is at least one branch where we actually knew the answer at this point. But I don't think that's true
right.
here. So if A is true, the output might be true or false. It depends on B. And if A is false, the output might be false or true. It depends on B. So
That's exactly right. So I guess in both cases, we still have to split on B.
okay, all right. So but now it should be relatively easy in the sense that there's a separate leaf for all possible inputs. And so we can just write the XOR function on the bottom. So if A and B are both true, then the output is false because it's exclusive. If A is true and B is false, then it should be true because A is true. If A is false and B is true, then it should be true because B is true. And if A and B are both false, then it should be false.
That's right. And by the way, if you were to think about it a little while, it would probably occur to you that this tree is just another representation of the full truth table.
Ah, very nice.
And in fact, if we wanted to do OR again, we could say, well, I was very smart last time, but I could actually write OR like this. And then just fill out the values at the bottom. If A is true and B is true, then yes. If A is true and B is false, then yes. If A is false and B is true, then yes. If A is false and B is false, then no. And this is a perfectly legitimate decision tree to represent OR because it basically is just another simple representation of the truth table. But as we pointed out when we did it last time, it's more of a decision tree than we actually need.
I can see that.
Because in particular, we don't actually need this. All right, so this little difference here between writing out the entire truth table on the left, as we did for XOR, and not having to write out the entire decision tree on the right for OR, actually is going to turn out to matter when we try to do things either more complicated or with more attributes than we did for these simple AND, OR, and XOR. Would you like to see?
Yeah, that sounds really cool.
Beautiful. So we saw before when we looked at AND and OR versus XOR that in the case of AND and OR, we only needed 2 nodes, but in the case of XOR, we needed 3. The difference between 2 and 3 is not that big, but it actually does turn out to be big if you start thinking about having more than simply 2 attributes. So let's look at generalized versions of OR and generalized versions of XOR and see if we can see how the size of the decision tree grows differently. So in the case of an N version of OR, that is, we have N attributes as opposed to just 2, we might call that the any function. That is a function where if any of the variables are true, then the output is true. We can see that the decision tree for that has a very particular and kind of interesting form. Any ideas, Michael, about what that decision tree looks like?
So going off of the way you described OR in the 2 case, we can start with that. And you pick one of the variables, and if it's true, then yeah, any of them is true. So the leaf is true.
What happens if it's false?
Well, then we have to check what everything that's left. So then we move on to one of the other attributes like A2.
Mm-hmm.
And again, if it's true, it's true. And if it's false, then we don't know.
We'll look at A3.
Good idea. This could take some time.
Yes. Oh, that's actually an interesting point. Let's say if there were only 3, we would be done, right?
Right.
But wait, what if there were 5?
Then we need one more node.
What if there were N?
Then we need n minus 4 more nodes.
Right. So what you end up with in this case is a nice little structure around the decision tree. And how many nodes do we need?
Looks like 1 for each attribute, so that would be n.
N nodes. That's exactly right. So we have a term for this sort of thing. The size of the decision tree is, in fact, linear. In N. And that's for any. Now, what about an N version of XOR?
So XOR is if one is true but the other one's not true, then it's true. And if they're both true, it's not clear how to generalize that. So why not?
So, well, the usual general version of this we like to think of is parity. All parity is a way of counting. So there's usually 2 forms of parity that we worry about, either even parity or odd parity. So let's pick one. It doesn't matter. Let's say odd. I like that. We'll do odd parity. And all that works out to be in this case is if the number of attributes that are true is an odd number, then the output of the function is true. Otherwise, it's false. Got it?
Got it.
Okay, so how would we make that decision tree work?
Ooh. Well, we got to split on something, and they're all the same, so let's split on A1 again.
Okay. So what do we do if A1 is true versus being false?
We don't know much if A1 is true. We have to look at everybody else.
Right. So let's look at A2. What if A2 is true versus false?
Well, if A1 and A2 are true, then the output is going to be whatever the parity of all the remaining variables are. So we still have to do that.
Yep. And I'm already running out of room, so let's pretend there's only 3 variables. What's the output?
All right, so the far left, there's 3 trues, which is odd, so the output is true.
Yep.
The next leaf over, only 2 trues. A1 is true, A2 is true, but A3 is false. So that's 2 trues, which is even, so the answer is false.
Mm-hmm.
And is this pattern continuing? Then we've got, no, so then it's false again, because we've got 2 trues and a false to get to the next leaf.
Mm-hmm.
Then we've got 1 true to get to the next leaf, so that's true. Oh, that looks like XOR.
It looks just like XOR. In fact, each one of these subtrees is kind of a version of XOR, isn't it? Now what we have is we have to do the same thing on the right. So we got to redo A2, and we're going to be in the same situation before, and we're going to start drawing on top of each other because there's just not enough room. So what's the answer to the one on the very right, where all of them is false? All of them are false.
So that's an even number of trues. 0 is even, so that's false.
Okay. And so in the case where only A3 is true,
True.
it's true, and we just keep going on and on and on again. Now imagine what would happen. In fact, let me ask you, Michael, what would happen if we had 4 attributes instead of 3?
Then we'd be really tired of this game.
Yes, and I'm already tired of this game. So the question is,
We
can
get
you
a whole other level of this tree.
Yep, we have to, it just goes on and on and on, and nobody wants to think about it anymore. So how many nodes do you think there are?
Well, for 3, there was 1, 2, 3, 4, 5, 6, 7, which seems suspiciously like 1 less than a power of 2.
Mm-hmm. And that is exactly right. You need more or less 2 to the n nodes, or
2 to the n, maybe minus
1.
1.
Yeah. But let's just say big O of 2 to the n. Everyone watching this is a computer scientist, so they know what big O means. Okay, so you need an exponential, therefore, as opposed to linear. Number of nodes.
Gad.
Yeah, so you very, very quickly run out of room here. You very, very quickly have a really, really big tree because it's growing exponentially. So XOR is an exponential problem and is also known as hard. Whereas OR, at least in terms of space that you need, is a relatively easy one because it's linear. We have another name for exponential, and that is evil. Evil, evil, evil. And it's evil because it's a very difficult problem. There is no clever way to pick the right attributes in order to give you an answer. You have to look at every single thing. And that's what makes this kind of problem difficult. So just as a general point, Michael, I want to make is that we hope that in our machine learning problems, we're looking at things that are more like any than we are looking at things that are more like parity. Because otherwise, we're going to need to ask a lot of questions in order to answer the parity questions, and we can't be particularly clever about how we do it.
Though if we were kind of clever and added another attribute, which is like the sum of all the other attribute values, that would make it not so bad again. So maybe
That's
it's
true.
just a kind of bad way of writing the problem down.
Well, you know, what they say about AI is that the hardest problem is coming up with a good representation. So what you just did is you came up with a better representation where you created some new variable, let's call it b, which is just the sum of all of the a's, where we pretend that, I don't know, true is 1 and false is 0. This is actually a really good idea. It's also called cheating because you got to solve the problem by picking the best representation in the first place. But you know what? It's a good point that in order for machine learning to work, you either need an easy problem or you need to find a clever way of cheating. So let's come back and think about that throughout all the rest of the lessons. What's the best way to cheat? All right, so what that last little exercise showed us is that XOR, in XOR, parity, is hard, it's exponential. But that kind of provides us a little bit of a hint, right? We know that XOR is hard and we know that OR is easy, at least in terms of the number of nodes you need, right? But we don't know going in what a particular function is, so we never know whether the decision tree that we're going to have to build is going to be an easy one, that is something linear, say, or a hard one, something that's exponential. So this brings me to a key question that I want to ask, which is exactly how expressive is a decision tree? And this is what I really mean by this, not just what kind of functions can it represent, but if we're going to be searching over all possible decision trees in order to find the right one, how many decision trees do we have to worry about to look at? So let's go back and take the XOR case again and just speak more generally. Let's imagine that we once again have n attributes. Here's my question to you, Michael. How many decision trees are there? And look, I'm going to make it easy for you, Michael. They're not just attributes, they're Boolean attributes.
Thanks.
Okay? And they're not just Boolean attributes, but the output is also Boolean. Got it?
Sure. But how many trees? So it's I'm going to go with a lot.
Okay. A lot. Define a lot.
Define a lot. So, all right. Well, there's n choices for which node to split on first.
Yeah?
And then for each of those, there's n minus 1 to split on next. So I feel like that could be an n factorial kind of thing.
Maybe. I like that.
And then even after we've done all that, then we have an exponential number of leaves. And for each of those leaves, we could fill in either true or false. So it's going to be exponential in that too.
So let me see if I got that right. So you said we have to pick each attribute at every level. And so you see something that you think is probably going to be, you know, some kind of combinatorial question here. So let's say n factorial. And that's going to just build the nodes. That's just the nodes. But once you have the nodes, you still have to figure out the answers. And so this is exponential because factorial is exponential. And this is also exponential. So let's see if we can write that down. So let me propose a way to think about this, Michael. You're exactly right the way you're thinking. So let's see if we can be a little bit more concrete about it. So we have Boolean inputs and we have Boolean outputs. So this is just like AND, it's just like OR, it's just like XOR. So whenever we're dealing with Boolean functions, we can write down a truth table. So let's think about what the truth table looks like in this case. Right? So let's look at the truth table. So what a truth table will give me is, for the way a truth table normally works is you write out each of the attributes. So attribute 1, attribute 2, attribute 3, and dot, 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 and there's n of those, right? We did this a little earlier when we did our decision tree, when we were trying to figure out whether I was on a hot date or not. And then you have some kind of output or answer. So each of these attributes could take on true or false. So one kind of input that we might get would be, say, all trues, right? But we also might get all trues except for one false at the end. Or maybe the first one's false and all the rest of them are true, and so on and so forth. And each one of those possibilities is another row in our table. And that just can go on for we don't know how long. So we have any number of rows here, and my question to you is, how many rows? Go. So we're back. What's the answer, Michael? How many rows do we have?
So if it was just one variable we're splitting on, then it can either be true or false, so that's 2 rows. If it was 2 variables, then there's 4 combinations, and 3 would be 8 combinations. So generalizing to n, it ought to be 2 to the n.
That's exactly right. There are 2 to the n different rows. And that's what always happens when we're dealing with, in Boolean attributes. There's always 2 to the n possibilities. Okay, so that gets us halfway there, and that gets to your point about combinatorial choices among the attributes. But that's only the number of rows that we have. There's another question we need to ask, which is exactly how big is the truth table itself? All right, so here's the question for you. We know that we have 2 to the n different possible instances that we might see. That is, 2 to the n different ways we might assign values to all of the attributes. But that still doesn't tell us how many decision trees we might have or how many different functions we might have. So if we have 2 to the n rows, here's my question. How many different ways might we fill out this column over here of outputs? Remember, an output can be either true or false. Go. Okay, Michael, what's your answer?
All right, so again, a lot feels like a good answer. It's already written down on the left. But it's also, maybe we can quantify this. So if it were, maybe one way to think about this is if each of those empty boxes there is either true or false, it's kind of like a bit. And we're asking how many different bit patterns can we make? And in general, it's 2 to the number of positions. But here the number of positions is 2 to the n. So it ought to be 2 to the 2 to the n. Which, is that the same as 4 to the n?
No.
Okay.
But you're right. It's 2 to the 2 to the n. So it's a double exponential. And it's not the same thing as 4 to the n. It's actually 2 to the 2 to the n. Now, how big of a number do you think that is, Michael?
I'm going to go again to my go-to place and just say a lot.
It is, in fact, a lot. And I'm going to look over here and I'm going to tell you that for even a small value of n, this gets to be a really big number.
So for 1, it's 2 to the 2 to the 1, which is 4. That's not a big number.
That's true. What about 2?
For 2, it's 2 to the 2 to the 2. So 2 to the 2 is 4, so it's 2 to the 4, which is 16.
What about 3?
All right, so that's 2 to the 8th, which is 256.
Mm-hmm. So that's growing pretty fast, don't you think?
Sure, but those aren't big numbers yet.
What if I told you that for n equals 6, 2 to the 2 to the n was, I'm going to start writing it, okay?
Ready.
1, 8, 4, 6, 6, 7, 4, 4, 0, 7, 3, 7, 0, 9, 5, 5, 1, 6, 1, 6.
Holy monkeys.
Yes, that is in fact the technical term for this number. It's a holy monkey. It is a very, very big number. So 2 to the n grows very fast. We already called that evil. 2 to the 2 to the n is a double exponential, and it's super evil. It grows very, 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 very fast. So what's the point of this exercise, Michael? It's to point out that the space of decision trees, the hypothesis space that we've chosen, is very expressive because there's lots of different functions that you can represent. But that also means we have to have some clever way to search among them. And that gets us back to our notion of an algorithm where it's actually going to very smartly go through and pick out which decision tree. Because if we aren't very smart about it and we start eliminating whole decision trees along the way, then we're going to have to look at to billions upon billions upon billions upon billions upon billions of possible decision trees. So now we have an intuition of best and how we want to split. We've looked over Michael's proposed sort of high-level algorithm for how we would build a decision tree, and I think we have enough information now that we can actually do a real specific algorithm. So let's write that down. And the particular algorithm that Michael proposed is a kind of generic version of something that's called ID3. So let me write down what that algorithm is and we can talk about it. Okay, so here's the ID3 algorithm. You're simply going to keep looping forever until you've solved the problem. At each step, you're going to pick the best attribute, and we're going to define what we mean by best, or a couple of different ways we might define best in a moment. And then given the best attribute that splits the data the way that we want, it does all those things that we've talked about, assign that as a decision attribute for node. Then for each value that the attribute A can take on, create a descendant of node, sort the training examples to those leaves based upon exactly what values they take on. And if you've perfectly classified your training set, then you stop. Otherwise, you iterate over each of those leaves, picking the best attribute in turn for the training examples that were sorted into that leaf, and you keep doing that, building up the tree until you're done. So that's the ID3 algorithm, and the key bit that we have to expand upon in this case is exactly what it means to have a best attribute. All right, so what exactly is it that we mean by best attribute? So there are lots of possibilities that you could come up with. The one that is most common, and the one that I want you to think about the most, is what's called information gain. So information gain is simply a mathematical way to capture the amount of information that one gains by picking a particular attribute, funnily enough. But what it really talks about is the reduction in randomness over the labels that you have with a set of data based upon knowing the value of a particular attribute. So the formula is simply this. The information gain over S and A, where S is the collection of training examples that you're looking at, and A is a particular attribute, is simply defined as the entropy, with respect to the labels, of the set of training examples you have S, minus sort of the expected or average entropy that you would have over each set of examples that you have with a particular value. Does that make sense to you, Michael?
So what we're doing, we're picking an attribute, and that attribute could have a bunch of different values, like true or false, or short, medium, tall.
Right, and that's represented by V.
Okay, each of those is a different V, and then we're saying, okay, for over those leaves, we're going to do this entropy thing again, and we, right. So what is entropy?
Entropy. So we'll talk about entropy later on in the class in some detail and define it exactly and mathematically. And some of you probably already know what entropy is, but for those of you who don't, it's exactly a measure of randomness. So if I have a coin, let's say a two-headed coin that could be heads or tails, and I don't know anything about the coin except that it's probably fair, if I were to flip the coin, what's the probability that it would end up heads versus tail?
A half.
It's a half, exactly. If it's a fair coin, it's a half. Which means that I have no basis going into flipping the coin to guess either way whether it's heads or it's tails. And so that has a lot of entropy. In fact, it has exactly what's called 1 bit of entropy. On the other hand, let's imagine that I have a coin that has heads on both sides. Then before I even flip the coin, I already know what the outcome is going to be. It's going to come up heads. And so what's the probability of me coming up with heads? It's
1.
1. So that actually has no information, no randomness, no entropy whatsoever, and has 0 bits of entropy. So when I look at the set of examples that I have and the set of labels I have, I can count the number that are coming up, let's say, red X's versus the ones that are coming up green O's. And if those are evenly split, then the entropy of them is maximal. Because if I were to close my eyes and reach for an instance, I have no way of knowing beforehand whether I'm more likely to get an X or I'm more likely to get an O. On the other hand, if I have all the X's in together, then I already know before I even reach in that I'm going to end up with an X. So as I have more of one label than the other, the amount of entropy goes down. That is, I have more information going in. Does that make sense, Michael?
I think so. So, is there? Maybe we can say what the formula is for this, or
Sure. What is the formula for it? You should remember.
it's if we have. Well, I'm not sure what the notation ought to be with these S's, but it has something to do with log p log. Wait, no, sorry, p log p.
So the actual formula for entropy, using the same notation that we're using for information gain, is simply the sum over all the possible values you might see of the probability of you seeing that value times the log of the probability of you seeing that value times -1. And I don't want to get into the details here. We're going to go into a lot more details about this later when we get further on in the class with randomized optimization, where entropy is going to matter a lot. But for now, I want you to have the intuition that this is a measure of information. This is the measure of randomness in some variable that you haven't seen. It's the likelihood of you already knowing what you're going to get if you close your eyes and pick one of the training examples versus you not knowing what you're going to get if you close your eyes and you picked one of the training examples. Okay?
All right. So, so then in the practice trees that you had given us before, it was the case that we wanted to prefer splits that I guess made things less random, right? So if things were all mixed together, the reds and the greens, after the split, if it was all reds on one side and all greens on the other, then each of those two sides would have they'd have low entropy, even though when we started out before the split, we had high entropy.
Right, that's exactly right. So if you remember the three examples we had before, one of them, it was the case that all of the samples went down the left side of the tree. So the amount of entropy that we had didn't change at all. So there was no gain in using that attribute. In another case, we split the data in half, but in each case, we had half of the X's and half of the O's together on both sides of the split, which means that the total amount of entropy actually didn't change at all, even though we split the data. And in the final case, the best one, we still split the data in half, but since all of the X's ended up on one side and all of the O's ended up on the other side, we had no entropy or no randomness left whatsoever, and that gave us the maximum amount of information gain.
So is that how we're choosing the best attribute, the one with the maximum gain?
Exactly. So the goal is to maximize over the entropy gain. And that's the best attribute. So we've got a whole bunch of trees we have to look at, Michael, and we're going to have to come up with some clever way to look through them. And this gets us back to something that we've talked about before, which is the notion of bias, and in particular, the notion of inductive bias. Now, just as a quick refresher, I want to remind you that there's two kinds of biases that we worry about when we think about algorithms that are searching through space. One is what's called a restriction bias, and the other is called preference bias. So a restriction bias is nothing more than the hypothesis set that you actually care about. So in this case, with decision trees, the hypothesis set is all possible decision trees. Okay? That means we're not considering y equals 2x plus 3. We're not considering quadratic equations. We're not considering non-Boolean functions of a certain type. We're only considering decision trees and all that they can represent and nothing else. Okay? So that's already a restriction bias. And it's important because instead of looking at the infinite number, uncountably infinite number of functions that are out there that we might consider, we're only going to consider those that can be represented by a decision tree over in all the cases we've given so far, discrete variables. But a preference bias is something that's just as important, and it tells us what sorts of hypotheses from this hypothesis set we prefer. And that is really at the heart of inductive bias. So Michael, given that, what would you say is the inductive bias of the ID3 algorithm? That is, given a whole bunch of decision trees, which decision trees would ID3 prefer over others?
So it definitely tries, since it's making its decisions top down,
it's going to be more likely to produce a tree that has basically good splits near the top than a tree that has bad splits at the top, even if the two trees can represent the same function.
Good point. So good splits near the top. Right? And you said something very important there, Michael. Given two decision trees that are both correct, they both represent the function that we might care about, it would prefer the one that had the better split near the top. Okay. So any other preferences, any other inductive bias on the ID3 algorithm?
It prefers ones that model the data better to ones that model the data worse.
Right. So this is the one that people often forget. It prefers correct ones to incorrect ones. So given a tree that has very good splits at the top but produces the wrong answer, it will not take that one over one that doesn't have as good splits at the top but does give you the correct answer. So those are really the two main things that are the inductive bias for ID3. Although when you put those two together, and particularly when you look at the first one, there's sort of a third one that comes out as well, which is ID3 algorithm tends to prefer shorter trees to longer trees. Now that preference for shorter trees actually comes naturally from the fact that you're doing good splits at the top. Because you're going to take trees that actually separate the data well by labels, you're going to tend to come to the answer faster than you would if you didn't do that. So if you go back to the example that we went before, where one of the attributes doesn't split the data at all, that is not something that ID3 would go for, and it would in fact create a longer and unnecessarily longer tree. So it tends to prefer shorter trees over longer trees, so long as they're correct and they give you good splits near the top of the tree. All right, so we've actually done pretty well. So through all of this, we finally figured out what decision trees actually are. We know what they represent. We know how expressive they are. We have an algorithm that lets us build the decision trees in an effective way. We've done just about everything there is to do with decision trees. But there's still a couple of open questions that I want to think about. So here's a couple of them I want you to think about, and then we'll discuss them. So far, all of our examples that we've used, all the things that we've been thinking about for good pedagogical reasons, we had not only discrete outputs, but we also had discrete inputs. So one question we might ask ourselves is, what happens if we have continuous attributes? So Michael, let me ask you this. Let's say we had some continuous attributes. We weren't just asking whether someone was an animal or whether a human or whether it was raining outside, but we really cared about age or weight or distance or anything else that might have a continuous attribute. How are we going to make that work in a decision tree?
Well, I guess the literal way to do it would be for something like age to have a branching factor that's equal to the number of possible ages.
Okay, so that's one possibility. So we stick in age, and then we have 1.0. We have one for 1.1. We have one for 1.11. We have one for 1.111.
I see. All right. Well, at the very least, okay. What if we only included ages that were in the training set? Presumably, there's at least a finite number of those.
Oh, we could do that. We could just do that. Except, what are we going to do then when we come up with something in the future that wasn't in the training set?
Oh, right. Can we look at the testing set?
No, we're not allowed to look at the testing set. That is cheating, and not the kind of good cheating that we do when we pick good representation.
Okay, fair enough. Well, we could ranges. What about ranges? Isn't that the way we cover more than just individual values?
Give me an example.
Say ages, in the 20s.
Okay, so, how would we represent that with a decision tree? Let's say in the 20s?
Age.
How would we do that?
You could do like age, element sign, bracket,
20s.
20, 21, or 29, or 30, right paren.
Yeah, it's too much. Why don't I just say age is between let's see, greater than or equal to 20 and less than 30. And just draw a big oval for that. Right? So that's a range. So that's all numbers between 20 and 30, inclusive of 20, but not 30. Right?
Yep.
And what's good about that is that's a question. You are either in your 20s or you are not. So the output of that is actually true or false.
So I guess the good news there is that now we know how to evaluate attributes like that because we have a formula from ID3 that tells us what to do. But it seems like there's an awful lot of different ones to check.
Right, and in fact, if it's truly a continuous variable, there are in principle an infinite number of them to check. But we can do now the sort of cheating you wanted to do before. We could just look at the training set, and we could try to pick questions that cover the sorts of data in the training set. So for example, if all of the values are in the 20s, then there's no point of even asking the question. You'd start to split instead upon values that were, say, less than 25 or greater than 25. And you can imagine all kinds of ways where you might do that. You might look at all of the values that show up in the training set and say, well, I'm going to do a binary search. So I'm just going to create an attribute for less than half of whatever's in the training set or greater than half of whatever the range is in the training set. Does that make sense?
Yeah, that's clever.
Right. Thank you. I just made that up on the spot. Okay, so you do those sorts of things, and that's how you would deal with continuous attributes. So that brings me to the next question. I'm going to actually do this as a quiz because I want an answer from our audience. So here's the next question I want to ask you. Simple true or false question. Does it make sense to repeat an attribute along any given path in the tree? So if we pick some attribute like A, should we ever ask a question about A again? Now, I mean something very specific by that. I mean down a particular path of the tree, not just anywhere else in the tree. So in particular, I mean this. So I ask a question about A, then I ask a question about B, and then I ask a question about A again. That's the question I'm asking, not whether A might appear more than once in the tree. So for example, you might have been the case where A shows up more than once in the tree, but not along the same path. So in the second case over here, A shows up more than once, but they really don't have anything to do with one another because once you've answered B, you will only ever ask the question about A once. So my question to you is, does it make sense to repeat A more than once along a particular path in the tree? Yes or no? Answer the question. Okay, Michael, what's the answer?
So, all right, does it make sense to repeat an attribute along a path in a tree? So it seems like it could be no, in that, if we're looking at attributes like, is A true, then later we wouldn't ask again, is A true, because we would already have known the answer to that.
Right, and by the way, information gain will pick that up for you automatically.
It doesn't have to be a special thing in the algorithm. If you consider an attribute that you've already split on, you're not going to gain any information, so it's going to be the worst thing to split on.
Exactly.
All right,
okay,
but it seems like maybe you're trying to lead us on because we're in the continuous attributes portion of our show.
Okay, well, what's the answer there? Is the answer not also false?
Well, we wouldn't want to ask the same question about the same attribute. So we wouldn't have age between 20 and 30 and then later ask again age between 20 and 30. But maybe we'd want to ask, given that we're less than 20, are we teenagers or not? So we might have a different range on age later in the tree.
So that's exactly right, Michael. So the answer is no, it does not make sense to repeat an attribute along a path of the tree for discrete valued attributes. However, for continuous valued attributes, it does make sense because what you're actually doing is asking a different question. So one way to think about this is that the question, is age in the 20s or not, is actually a discrete valued attribute that you've just created for the purposes of the decision tree. So asking that question again doesn't make sense, but asking a different question about age does in fact make sense. So once you know that you are not in the 20s, you might ask, well, am I less than 20 years old, maybe a teenager? Or am I greater than 40, how old am I, 44? Greater than 44, in which case I'm old.
Though if you ask, the tree that you drew isn't quite right though, right?
Yeah, it is.
Because if you go down the false branch, it means you are less than 20.
No, I could be greater than 30.
Oh, good one.
Yes, I'm very clever. Or at least I accidentally got it right. One of the two, it's the same thing. Okay, so there you go. So we've answered the thing about continuous attributes. Now, here's another thing. When do we really stop?
When we get all the answers right, when all the training examples are in the right category, class.
Right, so the answer in the algorithm is when everything's classified correctly. That's a pretty good answer, Michael, but what if we have noise in our data? What if it's the case that we have two examples of the same object, the same instance, but they have two different labels? Then this will never be the case.
Oh. So then our algorithm goes into an infinite loop.
Which seems like a bad idea.
So we could just say, or we've run out of attributes.
or we run out of attributes. That's one way of doing it. In fact, that's going to have to happen at some point, right? That's probably a slightly better answer. Although that doesn't help us in the case where we have continuous attributes and we might ask an infinite number of questions. So we probably need a slightly better criterion, don't you think? So what got us down this path was thinking about what happens if we have noise. Why would we be worried about having noise anyway?
Noise anyway. Well, I guess the training data might have gotten corrupted a little bit, or maybe somebody copied something down wrong.
Right. So since that's always a possibility, does it really make sense to trust the data completely and go all the way to the point where we perfectly classify the training data?
But Charles, if we can't trust our data, what can we trust?
Well, we can trust our data, but we want to verify. The whole point is generalization. And if it's possible for us to have a little bit of noise in the data, an error here or there, then we want to have some way to be able to handle that possibility, right?
I guess so.
So what will we do? I mean, we actually have a name for this, right? When you get really, really, really good at classifying your training data, but it doesn't help you to generalize. We have a name for that.
Right. That sounds like overfitting.
Exactly. We have to worry about overfitting.
So you can overfit with the decision tree too?
Yeah. What, you don't believe that?
No. I was being naive. I mean, I know that you can overfit with the decision tree. I was just.
Okay. Yeah, but your is the that you usually give when you're like, I don't believe what you just said, Charles, but I'm gonna go along with it anyway because I have to get off the phone soon.
Fair enough. I'll try to have a different personality then.
Okay, that's step one. Have a different personality with maximal information gain. Okay, so we don't want to overfit. So we need to come up with some way of overfitting. Now, the way you overfit in a decision tree is basically by having a tree that's too big. It's too complicated, right? Violates Occam's razor. So what's a kind of, let's say, modification to something like ID3 to our decision tree algorithm that will help us to avoid overfitting?
Well, last time we talked about overfitting, we said cross-validation was a good way of dealing with it, which allowed us to choose from among the different, say, degrees of the polynomial.
Right.
So maybe we could do something like that. I don't know, try all the different trees and see which one has the lowest cross-validation error. Maybe there's too many trees.
Maybe, but that's a perfectly reasonable thing to do, right? You take out a validation set, you build a decision tree, and you test it on the validation set, and you pick whichever one has the lowest error on the validation set. That's one way to avoid it. And then you don't have to worry about this question of stopping. You just grow the tree on the training set minus the validation set until it does well on that, and you check it against the validation set, and you pick the best one. That's one way of doing it, and that will work perfectly fine. There's another way you can do it that's more efficient, which is you do the same idea of validation, except that you hold out a set, and every time you decide whether to expand the tree or not, you check to see how this would do so far in the validation set. And if the error is low enough, then you stop expanding the tree. That's one way of doing it.
So is there a problem in terms of, I mean, if we're expanding the tree depth first search wise, we could be looking at one tiny little split on one side of the tree before we even look at anything on the other side of the tree.
That's a fine point. So how would you fix that?
Maybe expand breadth first?
Yeah, that would probably do it. Anything else you can think of? Well, so you could do pruning, right? You could go ahead and do the tree as if you didn't have to worry about overfitting. And once you have the full tree built, you could then do you could do pruning. You could go to the leaves of the tree and say, well, what if I collapse these leaves back up into the tree? How does that create error on my validation set? And if the error is too big, then you don't do it. And if it's very small, then you go ahead and do it. And that should help you with overfitting. So that whole class of ways of doing it is called pruning. And there's a whole bunch of different ways you might prune, but pruning itself is one way of dealing with overfitting and getting you a smaller tree. And it's a very simple addition to the standard ID3 algorithm. So another consideration we might want to think about with decision trees, which you're not going to go into a lot of detail, but I think might be worth at least mentioning, is the problem of regression. So far we've only been doing classification, where the outputs are discrete, but what if we were trying to solve something that looked more like x squared or 2x plus 17 or some other continuous function? In other words, a regression problem. how would we have to adapt decision trees to do that? Any ideas, Michael?
So these are now continuous outputs, not just continuous inputs.
Right. Maybe the outputs are all continuous. Maybe the outputs are discrete. Maybe they're a mix of both.
Well, it certainly seems like our rule of using information gain is going to run into trouble because it's not really clear how you measure information on these continuous values. So I guess you could measure error some other way. Well, we're not. It's not error, right? It's trying to measure how mixed up things are. Oh, so maybe something like variance, because in a continuous space you can talk about, if there's a big spread in the values, that would be measured by the variance.
Oh, good. So what you really have here now is a question about splitting. What's the splitting criteria?
And I guess there's also an issue of what you do in the leaves.
Right. So what might you do in the leaves?
I guess you could do some sort of more standard kind of fitting algorithm. So like report the average or do some kind of linear fit.
There's any number of things you could do here. By the way, that's worth pointing out on the output that if we do pruning, like we did before, we have errors. We did actually say when we talked about that how you would report an output, right? If you don't have a clear answer where everything is labeled true or everything is labeled false, how do you pick? So something like an average would work there.
I don't know. I mean, it seems like it depends on what we're trying to measure with the tree. If the tree is we're trying to get as many right answers as we can, then you probably want to do like a vote in the leaves.
Right, which at least if the only answer is true or false, that would look a lot like an average, I guess. Right, so you do a vote. I like that. So we do vote. So if we do pruning, we do have to deal with this issue of the output somehow. And something like a vote makes sense. And here, when you have a regression, then I guess average is a lot like voting.
Yeah, in a continuous space.
Yeah. So either way, we're doing a kind of voting. I like that. All right, Michael, so that covers decision trees.
Excellent.
So since you're the one who's listening, you get to tell me what we've learned today.
Well, we learned about the decision tree representation.
Okay.
We learned the top-down algorithm for inducing a decision tree, and we called that ID3.
All right, so we got a representation. We got a top-down learning algorithm, ID3.
We learned about the expressiveness and the bias.
All right. So those are two separate things. We learned about the sort of expressiveness, and we learned about the bias of ID3.
And we gave one. So is this specific to ID3? We looked at one specific way of deciding on splits, which was to do this maximum information gain.
Right. So we talked about in general what are good attributes or what are best attributes. So information gain is one way of doing it. That's one example. And by the way, this notion of best attributes is something we'll end up returning to, sometimes explicitly and sometimes implicitly throughout the entire course.
And lastly, I feel like we talked about the problems with overfitting and how in the decision tree context you can prune back the tree to avoid overfitting.
Overfitting is an issue. Overfitting is always an issue, and we came up with a couple of strategies for dealing with overfitting in the context of decision trees. Okay, so we've learned everything there is to know about decision trees. There's nothing else to know.
Somehow I find that hard to believe.
Yeah, there's a lot there, and the students will get a chance to learn even more as they do the assignments.
Cool.
Excellent. All right, Michael, thank you.
Sure. Look forward to the next chat.